record now.
Okay, are we ready?
Yeah, you are good to go.
Great. Okay, sorry about that. Oh, okay. Right. Thank you everyone for being here, and thank you for the invitation. I'm very happy to be here with you on this early morning. Yes, what I'm going to talk about today is this paper, Entropy Bounds Epistemic. And I've been told that when papers have a question in the title, the answer is usually no. In this case, the answer is going to be I don't know. I think the question is not settled by the current evidence. So what I'm going to try to do in this talk is not argue for one particular answer to this question, but rather try to explain to you what I mean by this question, why I think it is interesting and potentially important. And perhaps in the question period, some of you will tell me what you think the answer to the question is. So I'm going to begin by giving some background on entropy bounds and what they are and what their history is. And then I'll describe two possible interpretations of the entropy bounds in terms of the light sheet postulate versus the surface postulate. I'll then discuss the general problem of learning about physics inside a region of space-time, which is going to motivate a possible epistemic way of thinking about the entropy bounds, which I'll contrast with the perhaps more intuitive ontological way of thinking about the entropy bounds. And finally, I'll talk about how all of this is connected to gravity and how gravitational issues might affect our interpretation of the entropy bounds. Entropy bounds have their origins in the Bekenstein-Hawking entropy. So some time ago, Bekenstein and Hawking both conjectured that the entropy associated with a black hole should be equal to A over 4gh bar, where A is the surface area of the black hole. And at the time, that was a fairly speculative conjecture, but since then we have accrued a significant amount of theoretical evidence, at least, to indicate that this is the correct entropy. Evidence for that comes in particular from the Hawking calculation of the black hole radiation. So it's now fairly well accepted that this probably is the correct entropy to assign to a black hole. But this Bekenstein-Hawking entropy does have consequences not just for black holes, but for other kinds of systems. That's because if you lower some arbitrary physical system into a black hole, that's going to cause changes to the entropy and the area of that black hole. And we can show that the resulting black hole will not obey the Bekenstein-Hawking entropy requirement unless the entropy of the system that we lowered into the hole has entropy is less than or equal to 2 pi ER over h bar, where R here is just the radius of the system. Moreover, we can also show that if the system is weakly gravitating, that means that its entropy must be less than or equal to A over 4gh bar again. So we get back to that sort of original form of the entropy relation. So that's a fairly striking result. And although it was originally calculated just for a weakly gravitating system, it has led to a sort of fairly bold conjecture to the effect that maybe this is just true for any region of space whatsoever. Maybe for any arbitrary region of space-time that you could single out, you're going to find that the maximum possible entropy of that region has an upper bound proportional to its surface area. So if that is correct, that would be quite intriguing and surprising. For a start, you might perhaps be surprised to learn that the entropy associated with a region of space-time has any finite bound. If we intuitively think of space-time as a continuum, then one might think that we could keep on adding information to a region of space-time more or less forever, and so there would not be expected to be a finite bound on the entropy of a region. Moreover, even if you do have some reason to expect a finite entropy, for example, if you think that space-time is discrete, so there are in fact limited sites for information storage in any region, nonetheless, you might naturally be expected to think that the entropy of a region in space would scale with its volume rather than its area, surface area, because entropy is usually an extensive quantity. It usually scales with volume, so one would naturally expect that the fundamental entropy content of a region would scale with its volume and not its surface area. So if, in fact, it does scale with surface area, there's something really striking and surprising about that. It seems like some entropy is somehow missing that we wouldn't otherwise expect to be there. Now, we can to some degree explain why we get this missing entropy based on the idea that if we add too much mass and energy to a given region of space-time, it's going to collapse to form a black hole, And that means that the set of possible states for a given region of space-time is a little bit less than you might naively expect if you weren't taking into account the possibility of forming a black hole. So that perhaps explains why the entropy scales with a bit less than the volume. But nonetheless, it doesn't really explain why it should scale precisely with the surface area in particular. That still seems quite mysterious and interesting, and so there definitely seems to be something that needs explaining here. Now, as a matter of fact, the strong entropy bound turns out to be not universally true everywhere in our universe. In particular, it is violated in regions of the universe in which space-time is undergoing some quite rapid and significant transition, such as cosmic inflation, gravitational collapse, and so on. But there is a covariant version of the bound formulated by Raphael Boussot, which does, as far as we can tell, appear to be true everywhere in our actual universe, at least at the semi-classical level. So Boussot's version of the bound takes the same form as the original bound. It says S is less than or equal to A over 4GH bar. But now, rather than associating that entropy S with the spatial interior of the region, we're instead going to associate the entropy S with a light sheet associated with a given two-dimensional surface. So a light sheet is defined as a set of null geodesics leaving the surface orthogonally with zero or negative expansion, which we just follow up until they intersect at what's called a caustic, or they meet at a singularity. And I think it's easiest to understand the notion of a light sheet based on an example. So let's consider the case where the relevant surface of area A is just a sphere. So we can see that there are going to be four possible classes of null geodesics leaving the surface of the sphere. There's going to be one class going into the interior of the sphere, pointing towards the future, another class going into the interior of the sphere, pointing towards the past, and then there'll be one class going to the exterior of the sphere, pointing into the future, and then another class leaving the exterior of the sphere, going into the past. So we've got four classes there. Which of those are going to have zero or negative expansion? Well, the requirement for zero or negative expansion is just saying that the geodesics or light rays should be either remaining at the same relative distance from each other or going closer together over time. So we can see that the geodesics leaving the sphere and going out into the exterior are not going to have zero or negative expansion. Those geodesics are going to be getting further away as they get further from the surface. But the geodesics going into the interior of the sphere are going to have negative expansion. They are getting closer together as they move further away from the surface. So that tells us that we've got two light sheets in this case. One is the set of geodesics going into the sphere into the future, and the other is the set of geodesics going into the sphere into the past. This example also helps us see why the covariant entropy bound is equivalent to the strong entropy bound in most ordinary cases. Because if you think about those light rays or geodesics going into the interior of the sphere, what's going to happen is that the light sheet will continue until they all meet at the caustic, which will be at the center of that sphere. And that means that those light rays or geodesics are clearly going to traverse every point in the interior of the sphere exactly once before they meet at the center. And that tells us that the entropy on that light sheet is, in most cases, just going to be the same as the entropy on the spatial interior of the sphere, if nothing is changing too quickly inside the sphere. So that explains why the covariant entropy bound is equivalent to the strong entropy bound in most situations, but it does diverge from it in these more dramatic cases like cosmic inflation and gravitational collapse. And in those dramatic cases, the covariant entropy bound is satisfied and the strong entropy bound is not satisfied. So because the covariant entropy bound is equivalent to the strong entropy bound in ordinary cases, it is surprising for exactly the same reasons as the strong entropy bound seems surprising. It seems to be less entropy than one would naively expect, and it is, again, perhaps surprising that this entropy seems to scale exactly with the surface area rather than with the volume or anything else. So the strong entropy bound caused a lot of interest when it was first put out, and it led to a lot of speculations, in particular about the information content of space-time or the number of degrees of freedom enclosed in some region of space-time. So in particular, it was used as motivation to argue that the number of degrees of freedom in an arbitrary region of space-time is in fact proportional to its surface area rather than its volume. And this in turn led to various lines of investigation that have developed into the research program on holography. So this is an important and interesting speculation, but we should be a little bit careful with the assumption that what the strong or covariant entropy bound is telling us is something about number of degrees of freedom. And that's because entropy in general does not straightforwardly count a number of degrees of freedom. Certainly an information theoretic entropy can be interpreted that way. If, for example, we consider a system which is producing some kind of output and we calculate the information theoretic entropy of that output, then we will find that the maximum possible entropy is something like the number of bits or sites for information storage in the output. But thermodynamic entropy is not so straightforwardly interpreted as counting a number of degrees of freedom. There are various different kinds of thermodynamic entropies, but for example, if the one we're dealing with is a Boltzmann entropy, then the Boltzmann entropy is not going to correspond to the number of degrees of freedom in the system unless there exists some macrostate of the system which is compatible with every possible microstate of the system. And that's a fairly non-trivial expectation. It isn't true for most ordinary kinds of systems that we deal with. And so it's not clear that we should think of entropy as counting degrees of freedom in this case. Moreover, keep in mind that the entropy bounds are derived as generalizations of the Bekenstein-Hawking entropy, and most of the arguments for the Bekenstein-Hawking entropy are based on thermodynamic considerations. So it does seem quite natural to think that the entropies we're dealing with are thermodynamic entropies and not necessarily information theoretic ones, in which case we should be cautious about the number of degrees of freedom interpretation. A further reason for caution is the fact that thermodynamic entropies are usually regarded as being observer dependent. The result you'll get when you calculate the entropy of a given system in thermodynamic terms depends on the way in which you coarse grain that system or the way in which you divide the possible states up into different macro states. And that division is going to be different for different observers depending on their observational capacities, the means they have available to them for manipulating the system, and so on. So again, you might think if what we're dealing with here are observer-dependent thermodynamic entropies, then it can't be the case that the entropy bound is counting some intrinsic property of the system, like the number of degrees of freedom, because what we're dealing with is something observer-dependent. So there are reasons to be a little bit cautious about this interpretation in terms of degrees of freedom, but Flanagan, Murrelf, and Wald do take into account these kinds of concerns. And their argument, as I've quoted here, is that although there is an apparent tension between the fact that these statements are supposed to have the status of fundamental laws, for example, fundamental laws about the number of degrees of freedom, and the fact that entropy is a quantity whose definition is coarse graining dependent, they think this tension is resolved by noting that the number of degrees of freedom should be an upper bound for the entropy F, irrespective of choice of coarse graining. So the idea here is that even if all the individual entropies we're concerned with are indeed observer dependent and relative to a choice of coarse graining, the entropy bound that we're talking about is not any one of those individual entropies. It is a universal bound that applies to all possible entropies that could be assigned by any observer. So the thought is that something like the number of degrees of freedom in the system is an observer-independent quantity, which necessarily constrains all of the observer-dependent entropies that one might assign, and therefore it does possibly still seem reasonable to interpret a universal bound on the entropies as reflecting an intrinsic feature of the system, like its number of degrees of freedom. So although I still think we should be careful about talking about leaping from entropy bounds to number of degrees of freedom, for most of the rest of this talk, I'm going to accept the idea that maybe entropy bounds do indeed reflect some number of degrees of freedom, and we're going to start to consider what those degrees of freedom might be or where they might be located. So perhaps the obvious way to interpret the entropy bound is to say that it's counting the number of degrees of freedom on the light sheet. After all, we get the entropy in question by integrating over the light sheet. So it looks like, in mathematical terms, what we're doing is counting degrees of freedom on a light sheet. And so this leads to an interpretation of the bound as telling us that the number of degrees of freedom on a light sheet associated with a surface of area A is bounded by A over 4gh bar. So that is perhaps the most natural or intuitive interpretation of the bound, but there has been a different interpretation proposed. This is what I call the surface postulate, and it involves arguing that what we're really counting here are the number of degrees of freedom on the surface itself. So in that case, the bound just tells us that the number of degrees of freedom on a surface of area A is or is upper bounded by A over 4gh bar. So this interpretation of the bound has been argued for by various people, including Ravelli and Smolin. And it seems to be the case that basically the idea is that most of the arguments for the Bekenstein-Hawking entropy in particular are based on exchanges of matter and energy across the surface. And so it seems like those kinds of arguments ought to end up telling us about properties of the surface and not the interior. And so in the Bekenstein-Hawking entropy case, we should interpret the entropy as pertaining to the surface and not to the interior, and thus generalizing that to the entropy bounds, which are essentially follow from that Bekenstein-Hawking entropy. That gives us reason to think that maybe the entropies in that case also apply to the surface and not to the interior. So that leads to this way of thinking about the entropy bound as just counted degrees of freedom on the surface. So if the surface postulate is the correct way of thinking about the entropy bound, that I think would be a little bit disappointing. The entropy bounds attracted all this interest precisely because they seem to be saying something quite dramatic about regions of space-time having less entropy content than you would naturally expect, whereas the surface postulate seems to just tell us that surfaces have exactly the entropy you would naturally expect. As soon as you have any reason to think that the entropy on a surface is finite, surely the natural conjecture to make is that the entropy is going to be proportional to the surface area. So there seems to be nothing at all surprising beyond the fact that it's finite about the surface postulate. So if that's the total content of the entropy bounds, they're perhaps less interesting than they initially seemed. But it's totally clear that the surface postulate can, in fact, be regarded as exhausting the content of the entropy bounds. And that's because if the entropy bounds were really just about the surfaces and not about the interior at all, and one would then think that it shouldn't really matter how we describe the interior. So in particular, it shouldn't matter whether we use the strong formulation or the covariant formulation. Those formulations are using the same surfaces and assigning the same entropies. They're just differing in how they identify the interior region to which their entropy is assigned. And we know that the strong and covariant formulations are different, and in particular, one of them seems to be true in our universe and the other one doesn't seem to be true in our universe. So it seems that the content of the entropy bounds can't be exhausted by a claim about surfaces. It also needs to include a claim about interiors as well. So that gives some reason to think that perhaps the light sheet postulate is in fact the correct way of thinking about the content of the entropy bounds. But on the other hand, the surface postulate also seems very reasonable and intuitively appealing. And so perhaps one natural thing to say here is that simply that both of these postulates are right. The number of degrees of freedom on a light sheet is or is upper bounded by A over 4gh bar, and the number of degrees of freedom on the bounding surface is or is upper bounded by A over 4gh bar. They just have the same number of degrees of freedom. But if it is true that light sheets and their bounding surfaces always have the same number of degrees of freedom, that itself is surely very striking and seems like something we would like to have an explanation for. So I'm now going to propose one fairly natural way you could explain this relationship between the number of degrees of freedom on a surface and the number of degrees of freedom on its associated light sheet. Sorry. So I want to start by noting that there's one sort of natural corollary of the surface postulate. If we accept that the number of degrees of freedom on a surface is generally bounded, that means that the rate at which information can pass through that surface is surely also bounded. That's because in all our current physics, information can be transferred in the signaling sense only via local interactions. And that suggests that in order for information to pass through a surface, that information needs to occupy the degrees of freedom on that surface while passing through it. And therefore, it would seem that the rate at which information can pass through that surface is going to be bounded by the number of degrees of freedom on that surface, which, according to the surface postulate, is A over 4gh bar. So with that in mind, I want to propose the following thought experiment. Suppose that you are given an opaque sphere and you are told that there is some completely new physics going on inside the sphere, different to anything we have previously known about. So your job is to establish the nature of the physics going on inside the sphere, but you're not allowed to open up the sphere and look at that physics. Rather, what we've done is we have attached N LEDs to the exterior of the sphere in some kind of grid-like pattern, like the picture shown here. And those LEDs are going to turn on and off corresponding to signals that they receive from the physics going on inside that sphere. So, and your job is to establish something about the physics inside the sphere based just on what you can see from the pattern of illuminations of those LEDs. So what are you going to do in that situation? Well, you have various options, but perhaps probably the most natural thing to do is to start keeping a record of the pattern of illuminations of the LEDs. And when you have enough data, you're going to start looking for patterns in those illuminations. You're probably going to try to write down some kind of time evolution law, which predicts the future states of the LEDs based on the current state, or perhaps on some set of past states as well. And you might very well just stop there once you've got your evolution law. And if you do that, clearly what you end up with is an effective description of the sphere and its physics, which assigns it a state space composed of no more than n bits or n degrees of freedom corresponding to the LEDs on the surface. So you naturally end up with a state space which has n degrees of freedom. You could, of course, try to do something more complicated. You might, for example, try to imagine what might be going on inside the sphere and to therefore make some speculations about what the physics is that is leading to this pattern of illuminations on the outside of the sphere. But even if you do that, it still seems fairly likely that you would end up with an internal state space with no more than n degrees of freedom, since that's all the information you can extract at a given time. And certainly, even if you do end up with some description having more than n degrees of freedom, it would seem that we could arrive at an equally simple description of the physics by switching to a description with a state space of n degrees of freedom, coupled with either some indeterminism or some non-Markovianity. So the sort of the upshot of all this is that under these circumstances, it seems very natural for you to end up with a description of the physics of the sphere, which has no more than n degrees of freedom, corresponding to the degrees of freedom on the exterior of the sphere. And moreover, that seems natural almost regardless of how many degrees of freedom there really are inside the sphere. Certainly, if there are many more degrees of freedom inside the sphere than you can see on the surface, nonetheless, it would still be quite natural for you to have end up with this description assigning n degrees of freedom to the interior. So what we obtain in this situation is something a bit like a natural entropy bound. There's a sort of bound on the accessible information in the sphere, and that leads to a bound on the state space that you assign to it as an external observer. So the point of this thought experiment is simply that, in some sense, we are always in this situation when we try to learn about the physics inside a region of space-time. We can't go inside the region. We always have to interact with the systems that we are studying through a two-dimensional bounding surface, and thus the information we can obtain about them is limited by the information that can emerge through that bounding surface. So if it is true that two-dimensional surfaces in general have a limited number of degrees of freedom on them, that is going to entail limitations on the number of degrees of freedom that we can find out about from the outside. And it's natural to expect that that would lead to certain bounds on the degrees of freedom that we would assign those systems in our description of their physics. Even if there are, in fact, more degrees of freedom than that, we are likely to end up with a state space that looks closer to the accessible state space rather than the total state space. So the thought here is that perhaps the entropy bounds could in fact reflect our epistemic limitations rather than intrinsic features of the underlying physics. We are limited in what we can access. That shapes the physics that we arrive at, and that looks like a potential explanation of the entropy bound. We are assigning regions of space-time entropies that reflect our access to them rather than their intrinsic content. Now, one objection you might make at this point is that I've constructed this thought experiment using a closed surface like a sphere. That's the most sort of intuitive case for the epistemic interpretation of the bound. But you might also think that there's a possibility of rejecting that interpretation by noting that the entropy bounds are also supposed to apply to open surfaces. That is, I can take some open surface like a screen, construct a light sheet from it, and the covariant entropy bound says the entropy on that light sheet is still bounded by the surface area of the screen, even though it is open rather than closed. And you might think that the sort of epistemic description I've given isn't going to apply in that kind of case, because if the surface is open, then information can just go around the outside to reach me. It doesn't have to go through the surface. However, note that in order to make use of information that goes around the outside of the screen, I'm going to have to already know the content of the region of space-time through which that information is passing, because otherwise I won't be able to interpret it correctly as giving me information about the content of the original region. So really, in that kind of case, what we ought to do is just extend our screen and our unknown region to cover the full region from which I'm allowing information to reach me. So in that case, we still end up with a scenario in which, in effect, all the information that arrives at me has to pass through some screen, and we'd expect, therefore, that the amount of information I can access is going to be bounded by the degrees of freedom on that open screen. So I think that although the closed surface case is perhaps more intuitive, nonetheless, the epistemic interpretation does potentially still work in the case of an open surface. So this epistemic interpretation of the entropy bounds draws on previously existing ideas from various areas of physics. In particular, the important role of two-dimensional surfaces in physics has been noted by various people. Crane, for example, notes that if we divide the universe into system and observer, the observer no longer measures the state of the system, but only that part of it which impinges instantaneously on the observer, which of course takes place through a two-dimensional bounding surface. And that led Crane to formulate a categorical version of quantum gravity based on surfaces. Similarly, Euckel's general boundary formalism, which is used in various approaches to quantum gravity, is based on the idea that surfaces have an important operational role in terms of our access to various physical systems. And so Euckel, for example, considers three-dimensional surfaces, which are temporally extended two-dimensional surfaces, which bound certain experiments that we're trying to describe. And he considers how those experiments can be described in terms of degrees of freedom on those surfaces. Finally, there's the whole domain of holography that we could refer to. I won't talk about holography in detail in this talk. But one way of formulating holography is to think of it as requiring that asymptotic tasks possible using the bulk dynamics should coincide with tasks possible using the boundary. And from that point of view, we can sort of see the relation between holography and various epistemic considerations, because in a sense, it seems very natural that observers like us would formulate physics which has the property that asymptotic tasks possible using the bulk dynamics should coincide with tasks possible using the boundary, because we ourselves can only perform tasks that are possible using the boundary through which we interact with these systems. And so there's sort of no point in our physics containing other tasks which are not possible using the boundary. The epistemic interpretation of the entropy bounds also has links to various epistemic interpretations of quantum mechanics more generally. So, for example, Speckens and Ravelli have both argued compellingly that various features of quantum mechanics can be understood as consequences of some kind of epistemic restriction. And the idea that we are limited in the information we can obtain out of a given region of space-time looks like exactly the kind of epistemic restriction that they are talking about. And indeed, we can sort of see how some features of quantum mechanics could emerge from that kind of epistemic restriction. So, for example, one would naturally expect to see some indeterminism in this kind of situation, because if there are extra degrees of freedom inside various regions of space-time that are not accessible to external observers like us, then various kinds of processes are going to look indeterministic to external observers like us, because we don't have access to the hidden variables in effect that would in fact determine their outcome. And so we do indeed get that kind of apparent indeterminism. You can also possibly see some connections to uncertainty relations. So in particular, if we imagine some particle and we think of its position uncertainty as corresponding to a region of space-time in which it is bounded, so we think of it as being contained in something like a sphere whose radius is equal to its position uncertainty, then evidently, as the position uncertainty decreases, the surface area of that sphere will also decrease, and thus the amount of information that can pass through that bounding surface is going to decrease. So that means that as the position uncertainty decreases, the uncertainty in any other quantity is going to increase because we can obtain less information through that bounding surface. So in particular, as the position uncertainty decreases, the momentum uncertainty is going to increase because it's going to be more difficult to obtain momentum information through that bounding surface. So that's a fairly heuristic argument, but the point is just to note that there seem to be interesting links between the kinds of epistemic restriction involved in the entropy bounds and the kinds of epistemic restrictions postulated by people like Spickens and Ravelli as explanations of various features of quantum mechanics. Okay, so with that in mind, I'm just going to give here a classification of possible views that you could take on the entropy bounds. So the first option is to take the epistemic view that I've just suggested, in which we say that the real number of degrees of freedom on a light sheet may be greater than the amount specified by the bound. And there are sort of two directions you could go with that. You could take a pragmatic view, which involves saying that there may, in principle, exist degrees of freedom beyond those allowed by the covariant entropy bound, but we will probably never know anything about them, and they will have no impact on anything we can observe. So in fact, we can just get on with physics as if they don't exist at all. The alternative is to take a more positive view, in which we say there may exist degrees of freedom beyond those allowed by the covariant entropy bound, and it may be important to take them into consideration when doing physics, even though we can't directly observe them or access them. They may still be important. So those epistemic interpretations can be contrasted with what is perhaps the more intuitive interpretation of the covariant bound, where we think of it as counting the real number of ontological degrees of freedom on a light sheet. So again, you can sort of take a pragmatic or positive direction there. The pragmatic direction would involve invoking some form of pragmatism or empiricism to say that since we can never have any information about degrees of freedom beyond the bound, we should just assume that there aren't any further degrees of freedom, but the bound doesn't have deep meaning beyond that. It's just a kind of pragmatic constraint. The positive version, meanwhile, would involve saying, no, the covariant bound really is some kind of fundamental constraint, or it follows from some aspects of the fundamental ontology, and therefore it might tell us something profound about the nature of our reality. So having classified those views, we can go out and find various people who seem to hold versions of these views. So in particular, it's arguably the case that a number of physicists hold what I would describe as a pragmatic epistemic view, at least with respect to the Bekenstein-Hawking entropy. So that's because, as noted by Doherty and Callender, physicists will generally talk as if entropy vanishes when it passes behind the event horizon of a black hole, because we can't gain access to it. And the system itself isn't vanishing under those circumstances. If you don't believe in a firewall, then presumably you think that when a system passes behind an event horizon, nothing happens to it. It's still there in space-time. It's just become inaccessible. So when we say that entropy is vanishing when it crosses the event horizon, we're implicitly adopting a pragmatic epistemic view where we're accepting that there may be additional degrees of freedom, but we're deciding to exclude them from physics on the basis that we just can't access them and they seem unimportant. So that pragmatic epistemic view of the Bekenstein-Hawking entropy at least seems fairly common. But on the other hand, a few people have argued for something closer to what I'd call a positive epistemic view, on the basis that it may sometimes be important to remember the existence of those additional degrees of freedom. So for example, Ravelli argues that the page argument, which is often used to motivate the black hole information paradox, is based on the fact that if the number of black hole states is determined by the area, then there are no more available states to be entangled with the Hawking radiation when the black hole shrinks. He then notes that if there are in fact more states available in a black hole than what's given by the Bekenstein-Hawking entropy, then the page argument for the information loss paradox fails. So the point Ravelli is making here is that if the entropy of the systems that pass inside the black hole is in fact still there, even though inaccessible, it's sometimes important to remember that that entropy is still there. If we don't remember the entropy is still there, we're likely to get paradoxes or things that appear impossible, where information just disappears because we have forgotten about this entropy that does in fact still exist in space-time. So Ravelli is arguing for a positive view in which we should actually remember that there exists this extra entropy, and it may sometimes be important to take that into account when doing physics. So that view seems to be espoused, again, at least in the case of the Bekenstein-Hawking entropy, by various people, including Smolin, Sorkin, and Ravelli. The alternative is what I've called the ontological view, in which we think of the entropy bound as counting the real number of ontological degrees of freedom on a light sheet. And this view does seem to be held by a number of people, particularly people who have gone down the route of using entropy bounds to motivate various holographic ideas. So, for example, Bousso himself, the originator of the covariant bound, does seem to hold what I'd call a positive ontological view of it. He argues that the bound's simplicity, in addition to its generality, makes the case for its fundamental significance compelling. So he seems to be arguing that it should be regarded as some kind of fundamental property of our fundamental ontology. The ontological views certainly seem perhaps intuitively appealing, but I think they are to some degree threatened by the possibility of an epistemic interpretation of the bound. The worry is that anytime we postulate an ontology which has the property that the number of degrees of freedom on a light sheet is bounded as given by the covariant bound, the worry is that maybe what we're doing there is just mistaking an epistemic constraint for an ontological one. We're assuming that the number of degrees of freedom that we can access is the true number of degrees of freedom, and thus we are potentially just missing out a bunch of physics that is not directly accessible to external observers. So although ontological views certainly have things that are compelling and attractive about them, the worry is that how can we really be confident that what we're doing is counting the true ontological number of degrees of freedom rather than being misled by our own epistemic limitation? Okay, just to sum up where we are so far, I sort of suggested two possible routes you could take to interpret the entropy bounds, the epistemic route and the ontological route. And with everything I've said so far, at this point, I personally would probably be inclined to lean towards an epistemic interpretation. The epistemic explanation seems to provide quite a satisfying and clean understanding of why we should see this very, very characteristic relation between the entropy on a surface and the entropy on the associated light sheet. But this becomes more complicated once we take into account gravitational effects. So I'm going to talk now about what the relation is between the entropy bounds and gravity and how that might change the interpretation. So the issue here is that the evidence for the entropy bounds is partly based on gravitational phenomena. We can do various calculations in certain situations to check whether or not the entropy bounds hold. And in many cases, what ensures that the covariant entropy bound holds is precisely some kind of gravitational effect. So, for example, Bousso emphasizes that the gravitational focusing theorem is important in preserving the covariant bound in many cases. If you write entropy costs energy, energy focuses light, focusing leads to the formation of caustics or intersections of geodesics, and caustics prevent light sheets from going on forever. So the point here is that the covariant entropy bound could not be true if gravitational focusing did not occur. We must have gravitational focusing if the covariant entropy bound is going to be right. And that means we can sort of potentially turn this reasoning around and note that if we take the covariant entropy bound as either a fundamental property of reality or as some kind of epistemic restriction, it then seems that at least some of the phenomenology of gravity could be derived from the bound itself. If we assume that the covariant entropy bound has to hold, we can immediately derive that something like gravitational focusing must occur, because otherwise the bound would fail in many cases. Indeed, Jacobson has a famous result in which he derives the whole of the Einstein equations from an entropy area relation with a very similar form to the covariant entropy bound. So that's not quite the same as the covariant entropy bound, but again, it's certainly compelling to see that there seems to be some deep link between the entropy bounds and the phenomenology of gravity. So that leads to an important question about whether we should think of the entropy bounds as explaining gravitational phenomena or vice versa. We clearly have a mathematical relation here. What should we say about the direction of explanation here? What direction is the explanation going in? Various people have commented on this question about the direction of explanation. So in particular, Churko et al. Criticized Jacobson's proof on the basis that they argue that the entropy area relation he is using should be understood as derived from a certain quantum field theory calculation, which tells us that the entropy, the entanglement entropy across a bounding surface is given by NA over L squared, where A is the area of the surface and N is the number of different species present. They then note that in order to get N to cancel to give a universal entropy area relation, what you have to do is invoke gravitational effect. Once you consider the effect of gravity, you can show that N will cancel out, and then you get a universal entropy area relation, which is what Jacobson needs to do his proof. So the worry here is that Jacobson shouldn't be using the entropy area relation to derive the existence of gravity, because you need gravity to get the entropy area relation in the first place. However, it sort of seems to me that what's going on here is just begging the question. Jacobson presumably would simply respond that that is not where the entropy area relation comes from. The entropy area relation should be understood as a fundamental constraint. And then, in fact, if we consider the entropy area relation as a fundamental constraint, we can derive that N must cancel in this way. So actually, this just ends up looking like another example of a case in which an entropy area relation or bound can explain certain gravitational effects. We can derive that gravity must work in such a way as to cancel out the dependence on N. So there doesn't seem to be any obvious non-question begging way to resolve this issue about which direction of explanation we should choose. We can sort of make the explanation work in either direction. It's not necessarily obvious which of these things should be regarded as fundamental. And indeed, Bousseau himself argues that there's good reason to think the entropy bound explains the gravitational effects rather than vice versa, because if we try to explain the entropy bounds by invoking various gravitational effects, what we find is that we have to invoke a large range of different gravitational effects in many different scenarios in order to explain the entropy bounds. And that leads to a sort of quite unsatisfying, disunified explanation where a bunch of random gravitational phenomena come together in different ways in different situations to produce the same bound in each case. Whereas if we just start from the entropy area relation or the entropy bound, then we can explain all of these gravitational phenomena based on this single, simple unifying physical principle in terms of the entropy area relation. So that looks like a compelling reason to think that, in fact, the entropy area relation or the entropy bounds should be regarded as more fundamental and the gravitational effects should be derived from them. I'm not necessarily arguing that that is indeed the correct direction of explanation. I think the question is not easily resolved based on our current understanding of physics, but I do think that both directions of explanation seem potentially open to us and not entirely unreasonable. So that observation has important consequences for how we should think about the covariant bound. So if we accept that the covariant bound is in some sense an explanation of various gravitational effects, that makes the epistemic interpretation of the bound look very odd indeed, because it means that if the bound really is epistemic, if it is a reflection of our epistemic limitations and the fact that we can't access all the information we might like to through bounding surfaces, and if the bound then explains various gravitational effects, it looks like we're compelled to accept that certain gravitational effects are themselves epistemic in character. They are consequences of our epistemic restrictions, rather than being sort of objective phenomena that exist in an observer-independent way. And that certainly would be a very extreme conclusion. Gravity seems, at least naively, like an extremely objective phenomenon. It seems like it has nothing to do with the presence of observers. It would be at least extremely counterintuitive to end up arguing that gravity is in fact an epistemic phenomenon. With that said, there is some precedent for arguments which are perhaps heading in the kind of direction suggested by an epistemic interpretation of the bound. So, for example, here I'm just repurposing an argument due to Susskind, which can be regarded as suggesting an epistemic interpretation of certain gravitational effects. So Susskind imagines a case where we have a screen with some area A, an object behind that screen with some area A prime, and both of those, we're going to suppose that the information content on the surface of both of those things is proportional to their area, with the same constant of proportionality as given by the surface postulate in each case. So that means that if gravitational focusing does not occur between the object and the screen, it follows that the area element on the screen will be smaller than the area element on the object, And thus, since both of them saturate the amount of information content as given by the bound, that means that not all of the information on a given area element of the object is going to be able to pass through the corresponding area element of the screen. And therefore, from the point of view of an observer observing the object through that screen, not all of the information about that object will pass through. And thus, if we think of perceived area as having something to do with the amount of information that we can obtain about the surface of a given object, it seems reasonable to conclude that in that case, the perceived area is going to be smaller than the real area. And in particular, the perceived area is going to look as though gravitational focusing has occurred, because only that amount of information that can pass through the screen. And so this is a fairly heuristic argument, and it would need further development, but it does at least provide some indication that there is potentially a viable epistemic interpretation of at least some gravitational phenomena. So although I think the consequences of taking this epistemic interpretation of the bound and using it to explain gravitational phenomena are somewhat extreme, it's at least conceivable that there could be some epistemic aspects to certain gravitational phenomena. The alternative is, of course, to take an ontological view of the bound. And in that case, if we still think of the bound as explaining various gravitational phenomena, what we get is potentially quite a nice way of understanding why we have certain kinds of gravitational effects. And in the ontological case, that does not require us to say that gravity is in any sense epistemic. So in particular, suppose we adopt some ontological interpretation of the bound, where we say that light sheets are really just alternative representations of their bounding surface. They have the same ontology, and therefore they have the same number of degrees of freedom. Well, in that case, we can straightforwardly derive that geodesics must be focused by matter, because otherwise the light sheets would sometimes contain more information than their bounding surfaces, and that is impossible if light sheets are just alternative representations of their bounding surfaces. So in that case, we get a fairly straightforward explanation of certain gravitational effects, and that potentially seems quite appealing. It should be noted that the deriving gravitational phenomena from the covariant bound is going to have to use various approximations. It will have to treat entropy as a fluid, for example. So this way of explaining gravitational phenomena would have the consequence that we have to regard gravity as some kind of approximate emergent phenomenon. And thus this line of argument would potentially fit in very nicely with the existing research program on emergent gravity, which again sees gravity as an approximate emergent phenomenon. So just to sum up, I have set out sort of two possible routes you could take in terms of interpreting the entropy bounds. You can take the ontological route, in which we think of the entropy bounds as counting the real number of degrees of freedom on a light sheet. Or you can take an epistemic route, in which we think of the bound as counting the number of degrees of freedom accessible to external observers, and thus you end up introducing various epistemic aspects into the physics of these kinds of systems. So my own view is that on the current evidence, both of these interpretations are certainly still viable. Before thinking about gravity, perhaps the epistemic approach looks more appealing, but once we take gravity into consideration, that to me makes the epistemic approach a little bit less appealing, and thus puts the approaches on a somewhat equal footing, at least from my point of view. So I think this question is still open, and I think this question is potentially quite important because it has significant consequences for what you're going to say about the state space of a region of space-time and how you should think about things like a quantum gravitational description of that region of space-time. So settling this question is potentially important for how we should think about doing things like quantum gravity, and therefore has quite significant consequences for the future development of physics. So with that, I guess I should stop talking, and I'd love to know if you have any questions, or if you think you know the answer to my question, I'd love to know that too.